So this is non-triviality of Heegner point 2. And now we are going to follow Cornu's preprint. Preprint is, or I'll give the reference. The reference for this talk is Christophe Cornu. It's Compte rendu de l'Académie des Sciences, the last volume, last edition, right? I mean, and the title is Non-triviality des points de Heegner. And this note au cras is a really good thing for one talk because it's just 3 pages. So we are just going to follow his exposition. So yeah, so I'll first explain the theorem and then discuss the proof. So actually, all these talks start in the same way. Let E over Q, that's over Q, be an elliptic curve. I should have defined a macro where I could put in the field as an argument. Okay, good. But now, so N is going to be the conductor. Yeah, pi is going to be a modular parametrization. It's unique up to multiplication by integers, but now we don't care. The only thing that we ask is that it is surjective, a modular parametrization. Okay. What else do we need? We also choose a quadratic extension of Q. So K is a quadratic, an imaginary quadratic extension. So let's say this is imaginary quadratic with a condition such that this N splits in the ring of integers of K. So this means that OK modulo N OK should be isomorphic to Z mod N Z squared as rings. Right? That is, so this means exactly that the primes in N are split in K. And we choose a splitting somehow. So curly N will be an ideal such that OK modulo N is as a ring the same as Z mod NZ. Right, this is possible then. So there are 2 to the R choices if R is the number of prime factors of N. Right, that is this is somehow what the Chinese remainder theorem tells you. So yeah, we have also, okay, so oops, yeah, so this is what we fix now. We also fix some more notation for C greater or equal 1. So we are going to take this prime to N, put NC. This will be the intersection of N with this smaller order, right? But because we do this at a prime, I mean the ideal is prime to C, this is still an invertible ideal. Right, this is a locally principal ideal because I avoid the places where this ring is not maximum. So and for this, put this, and we also make a notation x index C. So this is a little c. This will be a Heegner point. So the Heegner point is C modulo OKC mapping to C modulo this, the inverse of this NC. Right? So the inverse is actually it's a fractional ideal that contains OK of C. So indeed you have this map to the quotient. And this is an isogeny that is a cyclic of, so this, yeah, because this contains OKC with a quotient Z mod NZ, this is a, what you call a cyclic isogeny of degree n. And so by what we have seen, well, this is inside x0n of C. We can view this as a complex point of the modular curve x0n. And this is called a Heegner point of conductor C. Okay. And maybe, yeah, okay, a Heegner point on x0n of conductor C. Now we can look a bit closer at the field of definition of this point. So actually, this x of C lies in x0n. We have this field Kc that we saw before the break, right? This is this extension of K where the Galois group is the Picard group. Maybe I should recall this, right? Okay, so K goes to Kc. This is Galois, and the group is the Picard group of OKC. Okay, so, and yeah, I recall also once more that this is unramified outside C, this extension. So it's abelian, unramified outside C, and this group is this Picard group. Now, I want to look a bit closer at this Picard group because we will take somehow the inverse limit over all the C's of the form P to the n for some prime P that we still have to choose. So, in the rest of the talk, K will be fixed, so I will drop it from the notation, and I will write just O of C, for example, right? So this K will disappear. So I want to study a bit better this Picard group. So the first thing is that we take a better look, say a geometric look at this ring OKC, O of C. So we have the ring O. This is the whole ring of integers. Right, and we can map this surjectively to O modulo C times O. Right, that is, and in O modulo C of O, we have the subring Z modulo C of Z. Right, that is, and yeah, and now there is the obvious thing you can do. You can take the inverse image of this subring in this ring. Right, that is and that is O of C. So this is what you would say a fiber product of rings. And so this is not geometric, but now we can try to think of the geometry behind this. Right? We can do spec, and draw a picture. So what does this picture look like, right? So it's like, so I like to compare this to a curve, right? This is an affine non-singular curve. And what we are doing is we are doing some pinching on this curve. So what happens here at a prime that divides C, what are we doing? So you have this curve here, say it's a regular curve, and I have this, I have a prime dividing C, so at P dividing C and not the discriminant of OK, of O, I really want to, I mean, I can draw a picture of this. It just means that we have, say this is a picture of O modulo P of O, or so. You see 2 points. Actually, it could be inert, but then geometrically there are 2 points. So my picture is geometric. And you just want to pinch, right? So this is what you do. You say, okay, I have this closed subscheme of the spec of this in spec of O. Inside, I mean, this is not on rings. On spectra, I have a map to spec of Z mod CZ, and I make a kind of push out of spectra, which means that I just get something like this. I mean, you you pinch these 2 points together. And this you can so say that this is the spec of O, you will call it X, and the spec of O of C, you call it X index C. You have a map here, say pi, this is the normalization map. And now we want to compute we want to relate these two Picard groups. So you have a short exact sequence of sheaves. On X of C, you have the multiplicative group of this. This goes inside the pi lower star of OX star. And as a quotient, you have, say, a kind of skyscraper sheaf at these points. Right? At these points, the function on the base curve are special for somehow functions here that have to have the same value in some neighborhood of that point. So you get a sequence like this. And if you take the long exact cohomology sequence of these sheaves on these spectra, you get the following interesting point. You get the unit group of OC, which is a very small group, right? And it's in this, and this goes to O. Yeah, now there is an interesting group, O modulo CO star modulo Z mod CZ star. This goes to the Picard group of OC, and this goes surjectively to the Picard group of O. So this is what this Galois group looks like, right? It sits in an extension of the Picard group of the whole ring of integers by mainly by this group, right? Because this is cyclic of order 2, 4, or 6. This is just something in there which contains at least, which is cyclic of at least order 2. And if my field K is not Qi or Q with the cube roots of unity, then actually I have already injection here, right? But so it looks like this. So yeah, that's what I. So now we're going to take a prime. Now let P be prime. P not dividing n. And we're going to look at the field K P infinity, which is the union over all n of K P to the n. Right, so, and I should also make a remark that now all the conductors will be of this shape. So if I write something with an n, it will mean conductor P to the n. So I had this point here, this Heegner point was called X index C, but I don't want to write all the time X and index P to the n. So let me just make the following remark that Xn will stand for, in the older notation, what was xp to the n, right? I hope you can deal with this. So from now on, because the conductors are concentrated at P, Xn will be the Heegner point of conductor P to the n. So now we take also the inverse limit of this sequence there to know what the Galois group is in the limit. So we have Z star goes to, let me see, yeah, goes to O star, right? If we goes to ZP tensor O star modulo ZP star, goes to this inverse limit over all n of the Picard of O P to the n, right? This is, and this limit we will call G, and this is the Galois group of K P infinity over K, and this surjects to the Picard group of O. So now we have a field extension K P infinity, and the group is this G, right? Here we have G. Now we can look at hom from G to ZP, because this business with Heegner points and this theorem of Cornu has to do with ZP extensions. So we should go make a ZP extension in there. And this hom, if you look at it, well, look at what this group looks like. This is a finite group. So if you hom it to ZP, that gives you 0. So look at here, right? This is up to something finite. This contains just one copy of ZP. And this is also finite. So it's not surprising that if you look a bit better, that you see that this is isomorphic as a group to ZP. Which means that there is a unique ZP extension in this, hence a unique ZP extension. And it's called the anti-cyclotomic ZP extension. Anti-cyclotomic. And it is like this, so we give it a name. We have H infinity in here. So here we have the group which is isomorphic but not so very canonically to ZP. And here we have a finite group G0. Because, as I said, well, except for this ZP, the other groups that occur there are finite. So it's finite. So that is the what it looks like, and this G0 is nothing else than just the torsion subgroup of G. So, oops. So that is not so complicated. So now I can, the theorem fits in this little space here. So this theorem by Cornu, which was a conjecture by Mesa, says that for almost all n, well, this is with one L, right? Almost all n. If I take the trace via the group G0 of pi of xn, so I'll recall what this means. This is in E of H infinity has infinite order. Infinite order. So that is the theorem. Is everything clear? Let me see. So pi was this modular parameterization. Xn was a point on x0n, so that is defined over H infinity. No, it's defined over K infinity, right? But the trace is exactly the sum of the conjugates over the group G0. So then you go from this field to this field. So that is why you get something in E of H infinity. So this, and now the theorem just says, okay, that this has almost always infinite order. So somehow I think this has to be thought about as a statement that says, well, maybe, for example, if the analytic rank of E is at least 2, Heegner points don't give, the standard Heegner points don't give you generators. I mean, don't give, they give torsion points, whereas, but if you look at higher Heegner points, these higher conductors are still useful, right? And if I understand it also correctly, if you can do a lot of things over this, because this is a ZP extension, there is theory to push results down sometimes. So this is why I think this has to do with Birch-Finit and Dyer. So then the proof of this. Right, so we start with a lemma. The lemma says that, well, this H infinity is a infinite extension of K, but the torsion over that, the torsion is finite. All right, and this is so usually for infinite extensions you have to be careful, because you can have a lot of torsion. So, but here the proof is quite easy, and it makes use of a so somehow this extension Kp infinity has some miraculous properties that most extensions don't have. So the thing is this, right? If I take for Q different from P prime and inert in K. So I take a prime that is inert in K. So K P infinity is completely decomposed at Q, which means that it's unramified and all the residue fields are of the same size as the residue field in K. I mean in O of K. So this, and because it is inert, this residue field is of order Q squared. So it just means that even though this is a huge big extension, at all primes that are inert in K and different from P, the residue fields are still finite, Q squared elements, which is, I think, very miraculous. The reason is just very obvious, because the description we have of this Galois group makes it like that. So the Galois group of K P to the n over K is nothing else than this Picard of O P to the n. And the Frobenius at Q corresponds to the class of the maximal ideal at Q. But this is the ideal Q times OP to the n. And obviously this is a principal ideal. So this is the zero class in this Picard group. Right? So if the Frobenius is trivial, that means that this is decomposed. So great. So you have, so we can do the following. We have O of K P infinity. We can look at the whole ring of integers. Actually, so I just, yeah, so actually I'm even proving stronger result. I'm doing this for K of P infinity, which is okay. It's a bigger field. So this surjects to FQ squared. And now it is known that if I look at the torsion over Kp infinity of my elliptic curve, this will map injectively to the torsion here, at least as far as the prime to Q torsion is concerned. Right? And here I have a finite group, so this lends it. So this means that the prime to Q torsion is finite, and if I choose a second Q, then I get all the Q torsion finite, right? All the torsion is finite, so use two different Qs. So that's it, right? So this was easy. So now we look at some map. So we will look at the following map. So we're going to look at x0n to the power g0. So this is just notation for the product of copies of x0n indexed by this group, by the elements of the group. We can just repeat this parametrization that many times. So we go to e to the g0, and then we take the sum map, sum to e. So this is all geometry. Now we're going to look at our Heegner points. So n now, so for an integer n, I send this to the point that I get from x index n. So this is sigma goes to sigma of xn. This is a point in this product. This and this, if I look where it goes exactly to the point that we want to have, because when we apply pi, this will just be pi of sigma of xn, but pi commutes with sigma, so it's pi of sigma xn. And anyway, we're going to sum, so we're going to sum the various conjugates. So this is just the trace over g0 of pi of xn. Right? And this is the point that the theorem was about. Exactly. So this is a map from n to e of h infinity. Right? So we have this map, and now we call it f. Oops. And the observation is to prove the theorem. The theorem, it is enough to prove that f has finite fibers, so that the fibers of f are finite. Right? This is because, well, there is only finitely many torsion points, if over these finitely many torsion points there are only finitely many points, then almost all points have image, not a torsion point. So this is the kind of reasoning I can do without thinking too much. Oh, I left my eraser somewhere. Where? No, I didn't. Oh, here. So now we have to think about how do we prove that the fibers are finite? And so somehow one has to distinguish two parts of this group G0. This G0 is a finite group, but there is a subgroup that is a kind of geometric subgroup, as Cornu says, I think, and then there is the rest is chaotic. Right? I should also say that the first proof of this theorem that he did was inspired by a proof of Watzal in the case where the quadratic field K was ramified at only one prime. Is that true? Or is
you relaxed it. So
he also relaxed it. Okay, but anyway, the first proof was based on with this principle saying chaotic, meaning that you apply a result from ergodic theory by Marina Ratner, and now this chaotic thing will be something like Zariski density in this version. So we have to. So basically, the problem is that it is not yet geometry. There is this map. So the sigma is the problem. So we have the sigmas in G0, and we have, so starting from a point xn, we have all these sigma of xn. Now, if this was given by some nice simple polynomial map that doesn't depend on n, then of course this is what you would call geometric. But as the Galois group, it doesn't act like this, right? So. But at least a part of it does. So let Q1 up to Qg be the primes ramified in K other than P. I don't know if P is ramified, but anyway, if P is ramified, I don't include it in the list of the Qi's. And then I can take the maximal ideals, the prime ideals over these. So these are the maximal ideals of O over the Qi. Okay, so now there is this simple observation again, which is the miraculous thing. That is that another miraculous property, I think, of this field Kp infinity is that the Frobenius at Qi, say I should write big Qi, has order 2 in G. So why is that, right? So it's again because of this identification between the Galois group and the Picard group. So the Frobenius at Qi corresponds with the class of the maximal ideal Qi in the Picard group of OP to the n, say, for every n. And if I square this, I mean, it's ramified of index 2, so this class squared, so Qi squared is Qi times OP to the n, right? So that's, again, the nice thing. I mean, the square is trivial. And itself, it was not trivial because it was really ramified. So this is of order 2, and even better, this G0, so it contains the group generated by these Frobeniae, and this group is the direct sum from IS1 to G. So what I claim moreover is that they are linearly independent. F2 times Frobenius at Qi. So this is also not so hard, because the only relation, well, this is not a proof, but if you multiply all the Qi's, then you get, of course, something that could be the thing of which you extract the square root. So that could be a principal ideal, but somehow, hey, that is strange. I thought that would not be true in this ring OP to the n. So why is that?
The Qi here you have to intersect it with OP and
Yeah, but still, right? If I take the Q1 up to QG, right? So suppose K is Q of root minus Q, say Q1, Q2 up to QG, right? Then isn't this the divisor of this thing? Isn't that exactly this? And oh yeah, but this is yeah, okay, good. This is why, yeah. So this is not in OP to the n, right? That is the point. This thing, because you see OP to the n are the elements that are modulo p to the n in z mod p to the n z. And this is not going to be modulo a high enough power. This is not going to be, so this thing is not in z, right? So also the difference with elements in z will be detected modulo powers of p to the n. Okay, good. So thanks. So we have this subgroup G1, and this G1 will account for what is called the geometric part. Okay, good. So, and to make, so what is claimed is that if I take the sigmas in this thing, in the group G1, then there is a definite a geometric description of that. And it is as follows. So we put n prime. We are going to make the level a bit bigger. It's going to be n times q1 times qg. Right? And this is still a square-free number, because the qi's were different from n was prime to n was unramified. And this is also prime to p. Right? That is because the qi's are different from p, and p was not dividing n. So n prime, this we can just take n times q1 up to qg. This also works. And so xn prime will be the point that corresponds to c modulo O p to the n mapping to c modulo this n prime, I suppose, p to the n, right? So have I explained that this n prime p to the n is just n prime intersect with O p to the n, right? This is the new Heegner point we will look at, and this thing is in x0 n prime k, oh, let's say kp to the n. Right, that's the same thing. So now, for 1 less or equal I less or equal g, we have the so-called Atkin-Lehner involution, WQI, acting as an involution on x0 n prime. Right? This is, I think, on the level of the upper half plane. This corresponds to the map tau goes to -1 over qi tau. No, it's not this. It's more complicated. Well then, anyway, I'll give you the moduli interpretation. It does this. If I have an elliptic curve f with subgroups G and H, so this is isomorphic to Z mod QIZ, and this is isomorphic to Z mod n prime over QIZ. So I just say, okay, to give one subgroup of order the product, because the product, these factors are relatively prime, is the same as giving two subgroups of these orders. And this I can send to the quotient of this elliptic curve f by g, and I need a subgroup of order qi, so I take f qi torsion modulo g, and h the image of H, right? That is, and if you, so somehow you can also do this in terms of isogenies. You can say to give this isogeny is to give one isogeny of degree n prime over qi and one isogeny of degree qi. Now you can take just the image of this isogeny of degree qi with as then you can fill up, make a square, so you also get there an isogeny of degree n prime over qi, and here you still have the dual isogeny back. This is what that does. So there's also that description makes it clear that if you do this again here, then you're back with this curve. So this is this involution. Maybe I should also say something that this involution, so if you have an eigenform on such a thing, then it is also an eigenform for this involution, and this explains somehow part of the L of the functional equation, right? You have your differential form, your modular form will be an eigenform for this, and if by Mellin transform you go to L functions, you find the functional equation. So you can also, if you do this for n prime, so you can also take the product of these things, you have a W n prime, and this gives you functional equation for the L function. So this is just, this was not mentioned, but it is useful to know. So, we have now 2 to the G degeneracy maps from x0 n prime to x0 n. So one way to explain what these are is just you have the usual map that forgets the subgroups of order q1 up to qg, but you can compose those, you can pre-compose them with each involution to the power 0 or 1. That gives you 2 to the G possibilities, right? And so that gives you these 2 to the G maps, and somehow they do the same thing as this group G1 with our Heegner point. So that's why it's geometric. So that is what I'll write down now. So delta, yeah, okay, so we have a map. So this parametrization pi that we had of our elliptic curve, we're going to, that was a parametrization by x0 n. We're now going to make one from x0 n prime. So we go to the x0 n to the g1, and this is delta, and this is just the product of these degeneracy maps. So here I have my 2 to the g copies of x0 n, and I have my map. This we compose with pi on each vector to e to the g1, and then we do the sum map to e. And if we look where our points go, so x n prime was this Heegner point. This goes to sigma of xn. So that's because we forget these. So here there is a little verification to do, that you really have to figure out that the Frobenius elements at these primes qi, well, actually they do this, but it's exactly what these degeneracy maps do. Right? There is a that you have to verify, and then yeah. So this goes to the trace over this group G1 of pi of xn, right? Because then we start to take the sum over these elements. So that's not really what we need, right? We wanted to have the trace over G0, which is a bigger group, but this part is what we get this way. So the rest of this thing is to get the trace over G0, well, you have to sum over a set of representatives for the cosets. So let R be a set of representatives for G1 contained in G0. So just and consider the following thing. So we have x0 n prime to the R goes with this pi prime to e to the R, goes with the submap to e, and now my n my integer is sent to a point that we call hn, right? And this hn, Heegner of n, is just sigma gives sigma of xn prime. And if you figure out where it goes, this goes to the trace over G0 of pi of xn, because the trace over this G1 is hidden in this pi prime. So this pi prime will do the trace over G1, and then if I sum over the conjugates by the elements in R, I will actually have summed over all the elements of G0, so I have this trace. Good. So now this is the same as our map F, right? So n goes to E of h infinity, and before this map was called F, and now we have it again, but with another description. And so now comes the funny thing. The link with the previous talk. So claim is as follows. Claim is that for I, an infinite subset of the natural numbers, for this infinite, if I take the image of, so if I take the let's say this map is called H, right? So I have the first part is H. So I apply H to this subset, I get a subset here. H of I is Zariski dense in where it should be x0 n prime to the R. Right, that is where it is Zariski dense. And this is the claim. So let's make a remark that this proves that F has finite fibers. Simply because if F had an infinite fiber, then I could take I that fiber, and this would really contradict the thing, because if a subset, well, then that is this H of I would not be Zariski dense, because if it were Zariski dense, then it would map, its image here would also be Zariski dense and not one point. So that is the...
You still need to show that pi prime is not trivial, but it's not constant.
Well, what is pi prime? Yeah. So where is pi prime? This is, it comes from, pi prime is here. So actually this sum here has a kernel, right? So you have the elements of sum 0. So why don't I land in there? All right. So Christoph, what do you say about that?
Sure that it's not constant here. Just sure that it's not constant. So we pluralize it. We get the map from E to each and one.
Yeah. So
G0 and G1. And then to G0 5 intercomponents is 0.
So this is the sum of all the degeneracy modes. Oh. Okay, well, I'll see that later, right? So I must show pi prime not constant. Okay, so we have to show that this is Zariski dense, right? And now, because of this talk before this one, it is enough. It suffices to prove the following thing. So anyway, I think if I mean, I can do that. So to reply to your question, if I prove that I have in the image of here a Zariski dense set, then I don't think that this can be constant, right? I mean, this is dominant here, and I take the sum. So that's another proof. There is a. Okay. So anyway, yeah. So that's good enough. Okay. So. Yeah, we have to prove the following thing. That is that because we know that Zariski closures, so I could say, okay, if I want, let's just look at the Zariski closure of this set. Then this is one of the sets that I talked about in my previous lecture. So if it is not everything, the reason for that is that there are two coordinates between which there is a modular equation, right? So let's just write that down. We have to prove the following thing. Suppose that we have sigma 1 and sigma 2 in G0. So I'm not looking really at these coordinates. I'm just saying, okay, suppose I have, because here I have elements R, right? So I'm just saying two elements in, I could have taken two elements in R, but I'm going to say, take two elements in G0, and that we have an M greater or equal 1, such that I look at the pairs, the following pair. So I take the J invariant of sigma 1 of this xn prime, and I take the J invariant of sigma 2 of xn prime. And this is in C2, and suppose that this lies on our modular curve x0m, right? Which is in C2, say. Right, well, I should say ρ0 of m, right? So inside C2 I have this Hecke correspondence with isogenies of degree m, and suppose it lies in there, right? This is the kind of equation that can occur for infinitely many n. Okay, then we have to show that sigma 1, sigma 2 inverse is in G1, right? Because that is exactly saying that these two elements, if they were different, well, that it means that it cannot happen if I take two different coordinates here, because two elements in R that are different will not have this relation. Right, so that's what we are going to show, and it works out. Pretty fine. So I want to show that actually there are, this claim here. So what happens if I have a lot of isogenies between the two different coordinates? So I want to have a lemma about isogenies. And the lemma says the following. So let E1 and E2 have Cm by K. Say that we have endomorphisms of EI is O of Ci. So now I reverse to the notation where, oh, this is the same notation as I used. But so this lemma is a bit more general than the situation in which I was. Let F from E1 to E2 be a cyclic isogeny, cyclic degree D, say. Then one has a factorization as follows. You can say, okay, this E1 goes with an F to E2, but we can first go with an F1 to something that I would write OC prime tensor OC1 over OC1 with E1, and here I can do a similar thing, but I want to dualize it, say with OC prime tensor OC2 with E2. And here we have an isogeny that we will call F prime, and the degree of F prime is prime to C prime. And I still have to write a little bit. The C prime is going to be C1 divided by the degree of F1. And this is the same as C2 divided by the degree of F2. Right, so there is a lemma like this that says that what isogenies between elliptic curves with CM look like. And I'm not going to write down the whole proof of this. This is in the appendix of Cornu's article. So let me just say why this should be true. So you have to. So basically, you can work prime by prime. You're thinking about isogenies between elliptic curves. So this is thinking about lattices in the homology over Q of the elliptic curve. Or you can also say this is thinking about lattices in the elliptic cohomology for every L. So for every L, and what I say is that it is completely, you can do it prime by prime, because suppose I do an isogeny of degree of some, say, prime degree L, then this will, the prime to L torsion is then identified here and here. So exactly you have the, it's kind of really a transversal situation. You can do prime by prime. So proof, for every L, think of lattices in VL of E. So VL of E as defined in Oosterlee's talks, where E, and this is isomorphic to QL times tensor K, if you like, right? Because with our CM curves, the VL modulus is one-dimensional over this, over the endomorphism ring. And I want to have this, wherefore I want to take a kind of base curve which has endomorphisms by the whole ring of integers, right? If you do this, then so I'm just going to draw some, well, actually you can even say we want to think of cyclic isogenies, lattices up to homothetty, so up to QL star. And if you look at lattices in a two-dimensional vector space up to QL, so this is the familiar tree thing, right? It's this tree of lattices up to homothetty in an analytic vector space. What you want to see is the following. You can just describe it a bit like this. So let me draw a few graphs, and I'll say what I mean with it. If L is inert, you have your lattice of this elliptic curve here, say in the middle, and this corresponds with conductor 0 at L, right? And then you have L plus 1 neighbors, and they will have conductor 1 at L, right? Exponent 1, and then you have things like this. So and this goes on, of course, right? So the further you go away from this standard lattice, the bigger the conductor is going to be. And now you can see if you have an isogeny here, and you look at what happens, you split it up into, say, an L power isogeny and then the rest, then you will just move from one point in this tree to another point, and you will just see that when you do this, the conductor goes down, goes down, goes down, goes to a minimum, and then goes up, goes up, goes up. So when it is to the minimum, this is where you put this curve, and that's how it works. And you have similar pictures for when L is ramified or when L is split. So it just looks a little bit different. So then we come to the end. Using this lemma, we can now finish the proof. So let's finish the proof. Suppose now sigma 1, sigma 2 as above, and m as above, that we have this. Then we have infinitely many fn's from En to sigma 1 inverse, sigma 2 En of degree m, and with the endomorphism ring of En equal to O p to the n. So this is the situation we have, because we will, by hypothesis, that's what happens. Now we apply this lemma to it, right? So you factor this thing, this thing, this thing, but this has already degree m in this case, right? This thing. So this has a smaller degree. I mean, at least not bigger, because you factor it like this. So there are only finitely many cases for the degree of this, and also for the degrees here and there. And so that means that the degree of f1 and f2 are bounded, but the degree of f prime is prime to the conductor, and now the conductor is p to the n with n big. So this means that the degree of f prime is going to be prime to p, right? That is an important thing. So we get fn primes, say from En prime to sigma 1 inverse, sigma 2 En prime, of fixed degree, so independent of n, I mean, degree m prime, so it may be a divisor of m, but and this is prime to p. Okay. If n is sufficiently big, right? But anyway, I want infinitely many things, and that is... So, and now we can describe this isogeny, because this is, we have described how the Galois action acts. This is of the form mn inverse tensor over OP to the n. Oh, actually I should do it right correctly immediately. So what I say is we write this as mn intersect OP to the n minus, this is a bit small, n minus a. This I'll have to explain a bit. Inverse, so this is supposed to be the inverse of an ideal of this ring here. Tensor this En prime. And why is this so? So this is this p to the n minus a is somehow because there is an isogeny of maybe some power of I mean this is what the difference between the c prime and c1, right? This is accounts for the change in the conductor. So there is a fixed decay somehow, a difference with this. This a does not depend on n. This isogeny is given by the inverse of some ideal that is prime to p, and then it is the intersection of an ideal of the ring of integers with this subring. If you think about geometrically what happens, I mean you have your curve, there are some singularities, but your ideal is away from the singularities, so it's just, that's enough explanation to say that any ideal that is just the whole ring of integer, that is the whole ring here at the singularities, is actually the intersection of an ideal of the normalization with the the ring you have. So you can write it like this, and then this Mn is an ideal in O of index M prime, right? That's the thing. Okay. So actually we know even more. We know that O modulo Mn is isomorphic to Z mod M prime Z, right? It's just like this. Okay. There are only finitely many possibilities for this Mn, right? Because, I mean, in O you have just finitely many ideals with this property. So we may as well suppose that Mn is just independent of n. It's just one given ideal. Okay, now we have something very funny, because then in this Galois group, which is the inverse limit of the pKs of OP to the n, the class of this M, so this is what we are using now. If I apply my M as a Galois element, so I have this bijection between this identification between the pK group and the Galois group. So this meaning being the same as this on infinitely many levels n means that this is, as elements in this inverse limit, it's the same as sigma 1, sigma 2 inverse. And this is in the group G0, right, which is torsion. So that is a strange thing, because now I have an element, a maximal ideal in the ring O, so this has nothing to do with n, right? But if I look at its class after intersecting it with every OP to the n, I mean, it is killed by a fixed power independent of n. Now if you think that, and also I know that the quotient is cyclic, so now we can do some thinking. What are the possible primes that can occur in this so let me write it like this. So there is an R such that greater or equal 1, such that M to the N, so M to the R intersect OP to the N is trivial, is principal for every N, right? Now this, so I claim that this implies that M is of the form Q1 to the E1 up to Q, it only contains the ramified primes, QG to the EG, because suppose that it would contain, so first of all, it doesn't contain inert primes because the quotient is cyclic. So no inert primes. And why are there no split primes? Because if you have a split prime, then well, of course, at every level this is of finite order, but the element in O that makes this of finite order is not going to be an OP to the n for big N. So that is the proof. So actually, yeah, no, that is enough to show that. So no inert primes, because we know that O modulo M is cyclic, right? And no split primes, because well, anyway, if look at this power here. This has just, because suppose this has this, so I take for some n this is principal. Well, there is only 2 units normally in this group, in this ring, 1 and -1. So up to there are 2 generators of this. But then if this generator cannot be invariant under the complex conjugation, because its complex conjugate is actually in the other split ideal, right, at the same prime. So therefore, so the generator is not Galois invariant. And so the difference is not 0, and then if I make the difference, if I make n big enough so that the difference has image non-zero modulo p to the n, then I can claim that from that point on I get a contradiction. So there are no split primes because blah blah blah, what I just said, and then we're done, because M is like this, and this means that this M is in the group G1. G1 was actually the group generated by the Frobenius. So this means that this is in G1, this thing, right? And that is exactly what we had to prove. So that's the end, right? Thanks.